describe you how you can use the L matching networks to match the source and load impedance in order to allow the maximum power transfer. Okay, so if you have, for example, a two-element L matching network, so you can have a capacitor, which is a reactive element, or an inductor in series like this. Okay, so the thing is that you're going to use this topology. So if you have a capacitor and inductor like this, and over here you can have a load connected. It can be a resistive load, it can be a reactive load, whatever it is. So let's consider a resistive load, and then this network happens to be in between a voltage source, an ideal voltage source, or a current source. Okay, so this is a voltage source, so it has a volt. Let's call it source resistance Rs, and you have a load resistance on the other side as RL. Okay, and Vs is my ideal voltage generator. Okay, and usually in most of the cases Rs is not equal to RL, so you need to employ or use this L network. You see, it looks like an inverter L, right? This is called the L network. So you use this LC elements, which is passive lossless elements between the voltage source and the load in order to maximize the power transfer. Okay, it could be the other way around as well. You can have um, you can have a capacitor over here, for example. Okay, or you can have a inductor over here. Okay, instead. So it's again an L. Okay, or you can have a capacitor over here, inductor over here. So again, that's why they are referred to as, it's gone in the literature. They are commonly referred as L matching networks. So this terminology matching, most of you will know that this normally means the use of lossless or non-resistive networks between a signal source and the load in order to maximize the power transfer. Okay, so you have this source. Okay, consider this source having a finite resistance of Rs, and then you have a load RL. So RL and Rs are not equal. In that case, you don't have the power transfer, maximum power transfer. Okay, so what you do is in order to match this RL equal to Rs, in order to have the both source and load impedances or resistances equal, uh, the condition for the maximum delivery of the power can be derived from the expression of P load, or the power delivered to the load, because the voltage on the load can be obtained from the simple voltage division, RL over Rs into Vs. So this is your voltage at this node, load node, and so this is your V load over here, and the power is V squared over RL. So this is your power at the load. Okay, given the voltage generator Vs. So if you differentiate the expression with respect to RL, okay, so let's say assume that you have some graph like this and you're plotting the power. This is your P load versus call it Rs or RL or Rs, whatever it is. Okay, and you have a curve like this. Okay, with respect to Rs. So it turns out that maximum power is transferred when this Rs is equal to RL. Okay, so on either side of the curve, when Rs is not equal to RL, so over here you see Rs is greater than RL, or Rs is less than RL. In both of these situations, you see the power transfer is not maximum. Okay, so in order to maximize the power, you differentiate the curve, find the point where this gradient is 0. Okay, and then from there you can find this condition that the RL should be equal to Rs. So this is what we are after. Okay, and this is what the job of matching L network is. So it matches. So it happens between the source and the load. You have an L section over here. You have an L section matching section over here. So what it does is it matches the load to source impedances using the reactive elements only, or non-dissipative elements. Okay, so you have a L section between your source and the load. So again, in this expression, if you substitute RL equals Rs. Okay, the maximum power delivery can be found out to be equal to 1/4 of Vs squared. Okay, so that's your maximum power. So once this condition is, this is what we desire, we know this, this is what we require. So how to design, for example, how to design a two-element starting from a two-element L matching network? Well, you can have other topologies as well. You can have a pi matching network. Okay, so there could be another reactive element over here, or you can have a T matching network. Okay, pi looks like this. So instead of having a reactive element configured in L configuration, you can have pi configuration like this. So this looks like a pi. Okay, so this is a pi topology, and these reactors, they can either be inductive, capacitive, or a combination. Okay, so this is a pi network topology. Similarly, you can have a T network like this. This is a T network. So the difference is that the match at a certain frequency, it could be narrowband, it could be wideband. For example, for a pi network, as compared to T network, the match could be narrowband, which is more desirable characteristic of a matching network. So there are certain advantages, pros and cons associated with each network. You can have a double L network, but then at the expense of the bandwidth of the match. For example, what you are interested is to have a width frequency. For example, if this is your design frequency, F naught is a design frequency. It could be any frequency in the AM broadcast range or FM broadcast range, whatever circuits you're using. How much narrow band, how much narrow match it produces is a better selective. You can say more is a selectivity, or you see what you are after is the maximum power transfer. So you need maximum power transfer at a particular frequency, okay, not at all the other frequencies. So at this frequency, a narrow band is more preferable. Okay, in that case, you might want to look into the pi networks. Anyway, starting with the basics. For example, you see these topologies can be derived from the basic two-element L matching network. For example, if you go and combine two inverted L networks, okay, you can have an L network like this, and then another L network like this, okay, and having reactive elements over here. So whatever the combination of the series reactance is, it is combined to produce a pi. Okay, so there again, both a pi network can be obtained from an L network. Okay, so this thing can be translated into this thing. Similarly, if you invert this, if you have a network like this, another L network, two-element L network like this. So if you're going to combine, for example, this section, then it's a double L network. Okay, it's a double L network. It's not this one. Or if you are going to have a combination like this is an L network, right? Combine it with another L network, which is like this. It has a parallel reactance and a series reactance, again a two-element. So combining these two L networks, combining these two produces a T network like this. Okay, this is your T network, and this is your pi network. Okay, so the basic is the two-element L matching network. So let's try to understand how we can use this to match source resistance that is not equal to the load resistance. In this case, it's 1000. We have considered a 1000 ohm source resistance with a load which is of 10 ohms, pure resistive load. So how to use this lossless network? This XP is a parallel reactor, XS is a series reactor. It could be capacitor or inductor, doesn't matter. Or both could be inductor, both could be capacitive, right? And the trick is to place the parallel reactance. The parallel reactance comes in parallel with the resistor that has a high value. So in this case, this is your R high. Okay, this is the high side of the resistance. So 1000 is more than 10. So and you place a series with a low resistance. Okay, so for example, if over here, if I interchange this resistance, I have 1000 over here, then I would have this parallel reactor connected in parallel in shunt with a high resistance. Okay, so wherever the high resistance is, either at the source side or at the load side, you connect your shunt or the parallel reactor with the high resistance. Okay, for the low resistance, you have the series reactor. Okay, so this is your R low. This is your R low. So the impedance, if you look on the left side of the circuit, you combine this 1000 with GXP, and you basically you do this algebra. You will find out that it has both real and imaginary parts. So if, for example, 1000 multiplied by JXP over 1000 plus JXP, and if you're going to rationalize this with, let's say, 1000 minus JXP in order to produce real and imaginary parts that can be separated. So you multiply and divide this by the same factor. Okay, 1000 minus JXP. So basically, what you get is this expression. Okay. So you see over here you have a imaginary part and you have a real part. So we can pick up a value of the parallel reactor. So the real part of Z left will be 10 ohms. You see, we are going to match, the idea is to match this left side with the right side. This is the left hand side of the circuit. Okay, so the parallel combination of JXP with 1000 is this expression. Okay, so it has both real and imaginary parts. So of course, if you're going to match this with the right hand side of the circuit, then the real part should be equal to 10 ohms. Real part should be equal to 10 ohms. And the since you have an imaginary part, it should be the negative of the series reactor. Isn't that right? Because we have to cancel this. We don't want the because the load is real in this case, and we don't need a reactance with it. So we can cancel XS compared to X left should be equal to, so this should be equal to minus XS. Okay, X left should be equal to minus XS, or XS is minus X left. Isn't that right? Because since we are using an L network, and the combination of a reactance with a real resistor produces an imaginary part. How do you take care of this imaginary part? Is that you select a series reactance, which is the negative of X left, and adding these two will give you the left hand side, which matches with the load resistor, that is a real load resistor of 10 ohms. Okay, so that's the idea. Now you see I have the same expression over here for the circuit that we have considered before. We have a 1000 ohm source resistance, if you need to match with 10 ohms. Okay, this is my Z left, okay, which has both real and imaginary parts over here. So we can bifurcate these two into imaginary and real parts. So real of Z left should be equal to 10 ohms. That's what we are after. We're going to match 1000 with 10 ohms, okay, through this L network. So the real part, this part of the circuit, the real part of Z left, so the real part of my Z left should be equal to 10 ohms to match with the right hand side. Okay, similarly, it will obviously it is going to produce the reactive part. So the reactive part can be set equal to minus X left. So considering the first equation, you see the XP is the only unknown, and XP comes in quadratic. So you have two roots, plus or minus. So this plus or minus implies you can either use, if XP is positive, it's a positive reactance, then it applies an inductor. If it is a negative reactance, of course it applies a capacitor. So you can use either an inductor or a capacitor depending on whatever sign you are using. So you can have a capacitor or inductor in parallel with a source resistance which is higher than either of these two resistances, and then you are left with the X left, and substituting this value of XP, which is found from this expression, you substitute this down into X left expression over here, XP. So what you get is 99.5, and you set your X left, you set your XS, the series reactor, equal to minus X left to cancel the the effect of the imaginary part of the Z left. Okay, so the left hand side has a correct equivalent series resistance 10 ohms, but then it is accompanied by the equivalent series reactance X left, and given by the imaginary part of Z left. So you can cancel this by inserting a series reactor which is equal to the negative of X left. Okay, so I hope I've made this point clear, because you are going to have a imaginary part and you're going to cancel it. And how you're going to cancel it? Just set your series reactor equal to the negative of X left, and that's it. You have matched your 1000 ohm source resistance, in this case, to a 10 ohm load resistance. Okay. So the final step is to find the values of inductor and capacitance that will produce the specified reactance at the given frequency. So suppose you're designing the circuit at the AM broadcast range, and near the top of the AM broadcast range is about 1.5 megahertz. So if this is your design frequency, then from this design frequency, you can find the inductance and the capacitance. So these two values of the reactors, they completely determine the source and load resistances. So except for the choice of which element is to be inductor and which is to be capacitor, there are no free parameters in this two element matching circuit. Okay, so either you can use a capacitor or inductor, it doesn't matter. You can use in two inductances as well. Okay, so but these has to be evaluated at the design frequency. In this case, it's 1.5. So once you have this values, inductor and capacitor, uh, I have this ADS schematic which is set up for the linear AC analysis of the circuit. This is a linear circuit, doesn't have any BJT or diodes. Okay, we are considering linear passive circuit elements throughout. If you're going to run this simulation over sweeping the frequency from 0 to 5 megahertz linearly and find out the power output, which is V out square over 100. 100 is my why it is 100. V square over it should be 10. Okay, it's not 100. It's 10. So V square over R is going to produce my P out, which is I'm interested in measuring with respect to the frequency. Okay, this is my inductance and capacitance L matching. This is my L matching network. Okay, and I'm interested to match 1000 ohm source with a 10 ohm resistor. Okay, so basically this is the same story. We have 1000 ohm source with a 10 ohm resistor. So these are the results of the linear circuit analysis. You see that the maximum occurs at about 1.5 megahertz over here. So we have the maximum power transferred. And then as you see, as the frequency is increasing thereafter, the effect of the capacitance, capacitive reactance takes over. Okay, you see the capacitive reactance is given by 1 over 2 pi fc. As the frequency is increasing, the capacitive reactance is decreasing, right? As frequency is increasing, this is becoming a short circuit. This is a short circuit, and inductor on the other hand becomes an open circuit. Okay, so in that case you are left with 1000 and 10 ohm, and you see at higher frequencies you have a very small at higher frequencies you have very small power transfer, because at this you're again starting having the mismatch. Similarly, at low frequencies the capacitor is open, capacitor and the inductance is short. Okay, the inductance XL is 2 by fc. Okay, so at frequencies around DC, the inductor behaves like a short circuit. Okay, so if this becomes a short circuit, that means the entire power is delivered to the ground from this side. It doesn't goes to the load. Okay, because this side is open due to the capacitor being open circuited at low frequencies. Okay, it doesn't couple the DC, so you don't have any power at DC. All right, at low frequencies no power is being transferred. So at the design frequency, whatever is desired, you have the maximum power. So that's how you design an L matching network, to have maximum power transferred to the load. Okay, at whatever the desired frequency is. So the match is perfect at the design frequency, but away from the frequency, we must accept the resulting frequency response. So we don't have any free play over in these regions at low frequencies or high frequencies regions. Okay, we must accept the response, but this is what we are after, and this is what we get. Okay, so we get the maximum power transfer at 1.5 megahertz. Similarly, you see here I use inductor, there it was a capacitor. So an alternative, this is an alternative L matching ADS schematic with L and C interchanged. So if you change, instead of inductance, you bring a capacitor over here, again, it's a reactive element, you can do that. It's your choice. You can have an inductor over here as well, okay? You can have two inductances. So there could be four combinations. You can have two capacitances. You can have a combination of C and L. So for a two matching L section, you can have four such networks, uh, four such L matching networks between the source and load impedances. Okay, so for this particular case, we have the match at the desired frequency, 1.5 megahertz, but at high frequencies there is no power transfer. Why there is no power transfer? You see, at high frequencies, the inductor is open circuit. Okay, so it behaves like an open circuit, and at high frequencies the capacitive reactance is as such that it becomes a short circuit. Okay, so the capacitor is basically shorted out over here. Capacitor is shorted. This is open circuit, so no power is being delivered to the load. Nothing. You don't get anything at high frequencies. At low frequencies, well, at low frequencies there is some power, but then you have a mismatch over here. Okay, at high frequencies there is no power that is being transferred to the load. This is mismatched frequencies. So this is the idea behind designing a simple two-element LC matching networks. You can go for pi network or T network topologies, but then again, we can talk about that in the other videos. They can be derived from these simple L matching networks, LC or CL. Okay. So again, this is what we desire.